Okay, so hi everyone. Today I'm going to be talking about BioMedGPT, which is a generalist vision language foundation model specifically made for a diverse biomedical task. So, as an image and text, it could take very much multimodal data like MRI, X-ray, EKG, any sort of modalities, not only image specifically. And for text, it can also be publication, EHRs, clinical notes as the input. So that is why it's called a generalist vision language model. Now, the problem they're trying to solve is, for example, there's this news in the US that a boy saw 17 different specialist doctors over 3 years for chronic pain, but ended up finding the diagnosis by ChatGPT. I think that's what they essentially want to solve. Since BioMedGPT is a transformer-based model designed to perform diverse vision, language, and multimodal tasks across different biomedical modalities, all within a single architecture. So the conventional medical AI now is considered as the specialist doctor. So it is very task specific and it is very modality specific. So it doesn't perform well in a multi-model and a generalist view. So is, for example, it's only tailored for X-ray or it's only tailored for text generation. Text generation. So there's the conventional medical AI is like this, but what their paper is trying to say that there is a way that we can combine all of this within a single architectures, and the architecture is based on transformers. Now, for every training foundation models, there's three main architectures. It's encoder only, there's decoder only, and both encoder and decoder. But they mention in the paper that both encoder and decoder only struggle to learn with multiple modalities. So in this architectures, they uh, apply the encoder and decoder architecture for BioMedGPT, which is they claim more adept at mapping various modalities into a unified semantic representation space. And here's a brief architectures of what the BioMedGPT looks like. So it can take a text encoder and a 2D or 3D image, depending on which encoder you use. And then they will concat them together and then throw it into the encoder and then to the decoder, and we will get this discrete output sequence which will we then can perform a downstream task to either of this specific task purpose, and it's being divided into three scale of small, medium, and the base model. They also create this unified vocabulary in which they combine all the text and the image and the bounding boxes using separate tokenizers or encoders. So for bounding boxes, they use pix to sec, and for text, they use BPE, and for image, they use VQGAN, which they claim at that time of their research is the best, but they also mentioned that uh, as it's always evolving, there's newer and more and better tokenizers that we can use now for this text, image, and bounding boxes. But they create this vocabulary and combine them together to handle this diverse modalities without relying on task-specific output structures. And the total is 59,400 something, which included 50, most of them as a language tokens, 1,000 location tokens, and 9,000, 8,000 vision tokens. And this is how the vocabulary is being used. So the original image will be passed into the tokenizer and they will get the visual tokens. And then it will be transformed into a sequence of patches. And then they perform random masking since it is a transformer model. So this is necessary steps to first synchronize the image into patches and then throw it into the encoder, the decoder, and then they will perform the predictions based on this visual tokens as the ground truth, I guess. And then they also modified the transformer models. So mainly, I highlighted what they modified. So they added three normalization operations to each layer. So there's a post-attention layer normalization, post-first feed-forward networks layer norms, and a headwise scaling within self-attention, which is just a modified first version of self-attention. And then they also changed some algorithm for the positional embeddings to create two sets of absolute position embeddings for both text and images. And then they also implement a new decoupling method to separate position correlations. Yeah, they say they made this algorithm to avoid any unnecessary randomness in the attention. They also incorporate a 1D relative position bias and 2D position bias for the image. So yeah, there was a text, and this is actually the image for better visualization. So this is the layer norms that they added in the paper just now, and this is the head scale self-attention. So this is just to compare with the vanilla transformer. So for the transformers, the input embeddings is just directly thrown into the attention model, but in the BioMedGPT, which is based on OFA uh, architecture, they first concatenate the text and the visual with the position embeddings, and then they perform layer normalization first, and then they throw it into the newly head scale self-attention. So the author did some in-depth review of why adding this normalization layers and adding this newly head scale self-attention could benefit the architecture, which is mostly to reduce the randomness inside the architectures. And for the Haskell self-attention, to compare with the vanilla attention architectures, it's basically all the same. It's just that after the matrix multiplications here, they added a new Haskell attention here. So this is also the formula that they come out with. And this is basically what they do for the Haskell self-attentions. For the position encoder I mentioned earlier, for the 1D relative position bias and the 2D relative position bias, the author also claimed that adding this relative positions helps the text and image understand relations better. So instead of just knowing that pneumothorax is two distance away from the no and there is two distance away from no, they also know that there is behind no and pneumothorax is in front of no. So they know the positions of the tokens, I guess. Same things goes for the 2D relative positions. And this is also the newly position embedding method that they use in the architectures, which they also promote will reduce randomness in their positions. So this is a quick look of how the performance for the BioMedGPT compared to BioMedClip and MedFit. We can see a decent performance boost here on image classification task. It achieves state of the art in almost all of the external dataset here, except for breast ultrasound. And some key points mentioned by the author that they achieved 16 state-of-the-arts out of 25 different experiments, even with limited data sets such as EEG, which only consists of 0.04% compared to like X-ray, which has almost 30%. And BioMedGPT is also very lightweight, but very powerful compared to MedPalm here. The result is almost similar or even better, but MedPalm model has 12 billion parameters, which BioMedGPT has only 182 million parameters, which makes it a very lightweight model, but very powerful. They also did some human evaluations with doctors. So they claim that they outperform LavaMed in terms of VQA, and it also can generate some report summarization better than LavaMed, I guess. It also achieved a satisfactory error rate of 8.3% in writing radiology reports. So I think according to the authors, doctors were very impressed seeing this BioMedGPT can output this kind of results. An extension of this model is they did try to extend this to a 3D for 3D image, which only requires integrating pre-trained 3D VQGAN or any 3D image encoder, and then adding a learnable 3D visual encoder to the pipeline. And then the author also mentioned that to further extend the models, yeah, we can focus on like non-text generations tasks like segmentation and introducing additional decoders such as mass decoder. Their limitation is being that since all of this modalities, there's a lot of modalities being trained, but it's kind of imbalance since there's a lot of X-rays, MRI, microscopy images, but there's very small amount of EEG, EKG, like this kind of stuff, which is rarely people take. So there's an imbalance going on here. So I think in the future, the writer also mentioned that as an extension of this model, we can further balance the data sets being used for the pre-trainings of the models. And then I think you can learn more at the, oh, sorry, you can learn, there's a YouTube which mentioned this BioMedGPT, which breaks down all the architectures and the reason why the authors had this kind of layers and why did they change this kind of architectures. It's available in YouTube, but it's kind of long videos, which some of the slides are also from this YouTube videos here, and there's also code that we can check out to further knows how the models work and how the training works since they published the GitHub publicly. Thank you. That's all from me today.
谢谢Ryan 哈，那个我实在是没有办法下什么 comment，就是，但我想我人在这边一直想的事情，大概也就是说，怎么能够把我们长庚的这些这么丰富的资料哈，在没有 label 的情况下哈，去做一些应用，所以我们一直有在做一些 visual language 的尝试，那前面都一直卡关，那有些也是 language 的地方还在学习，就是在摸索。那当然也有请教，比如说像古文伦老师，每次都念错。那所以当然这个不知道其他老师有没有什么 comment 不过我大概就是希望说，我们在走的过程中，像跟古老师在旁听他的课，跟他讨教的时候，他就是跟我们说，其实你 data 还没有整理好，你也不用太急着看 model，因为很快就有新 model 不过就是我自己从中间是有些学习啦。那我先问其他老师有没有什么 comment 好了，不要占这个大家时间太多。像那个徐老师、曾老师有没有什么对这个？因为这个本来是郑医师提的，只是他今天没有上来。那不知道那个曾老师和徐老师对这个题目有没有什么 comment，或者是范医师也在线上嘛？好，看起来大家是没有什么 comment。哎，应该还听得到我声音嘛？Ryan, you can hear me, right?
Yep.
听得到，纯粹只是没有办法下康妹而已。
好，OK，好，那这样，我觉得我们大家就是反正有新东西出来就 share 一下，然后那 Ryan, please also share your slide because you have a link here that we can do some homework, and maybe next time in January we can just chat more related to this one, or probably hopefully we will not have another one to read again. 所以我会请 Ryan 就 share 这个 slide，然后把他今天这一段录起来的，再给这个郑医师、魏医师看，或者张医师没有上来的。好，那如果没有的话，我们谢谢大家。今天我也学到很多，有很多功课可以做了，希望可以以后可以跟得上大家一起来多一点这个 technical 的部分有些贡献好，那我们今天就到这里咯，谢谢大家今天的参加，我们就1月份见，请大家祝大家这个